Hello everyone, here we'll be discussing chapter 8.1, which is a section on what is called law of sines. And, well, the first thing we need to talk about, of course, is the law of sines. Now, law of sines basically is some relationship between angles of a triangle and the side lengths of a triangle that, of course, involves the sine function. So it says here, if the triangle ABC has sides lowercase a, b, and c, with this kind of layout, which I'll talk about in a little bit, then the following must be true. A over sine of A is equal to B over sine of B is equal to C over sine of C. Now, of course, there's this whole notion between capital letters and lowercase letters. Now, the lowercase letters stand for the sides that are opposite of their angle capital counterparts. So here, angle capital A is opposite side lowercase a. And similarly with B and C. So you can kind of see that here. And I've drawn some two cases. Here we have an acute triangle, meaning all angles are less than 180. And here we have an obtuse triangle, meaning one of the angles is bigger than 90. I meant to say 90 here, not 180. Of course, since all angles in the triangle add to 180, they're all going to be less than 180. But acute means they're all less than 90. Obtuse means one of them is bigger than 90. So I can try to explain a little bit about why this is true no matter what type of triangle we have, just by kind of creating this height here. And if you consider, for example, sine of C is this height over A. Okay, so you can write sine of C is equal to H over A, but then similarly you can write sine of A is equal to H over C, and if you cross multiply, you end up getting this relationship between the C's and A's. To get the relationship between the B's and C's, you need to create some other height using another vertex, not B, but you'll get something similar. So I'm not going to go into too much of the proof, but I'm just kind of explaining more or less why it's true, just creating an altitude so we can get a right triangle involved, and we can see that this relationship works no matter what kind of right triangle we have, even if it's not a right triangle. In fact, for this obtuse case, we kind of have to extend outside of this. So we look at this angle here, and you call this height h, but we'll notice is that sine of C is h over a, and then sine of A, this is kind of funny, but remember what we saw from trig values at any angle. Here, this angle here is kind of representative of A, because A really is this obtuse angle, and you can think of this to be like A bar, which is the reference angle of that. And since sine is the same value in the second quadrant, then the sine of this obtuse angle must be the same as sine of this lowercase angle. In other words, sine here is h over, well, I guess it would be h over c in this case. So you actually get a very similar thing that we do here. Sine of a is h over c, here sine of c was h over a, exact same setup. You can cross multiply and get that same relationship between a's and c's, and then pick a different altitude, not using b as a vertex, and you'll get another relationship between b and c or b and a. So I hope that makes sense. And again, you can try to play around with that idea on your own and maybe develop a legitimate proof, but the proof is kind of based on this idea here. So now with some examples, we want to complete triangles, basically is what we're going to be doing. And again, completing a triangle here just means that we're finding all of the angles and all of the lengths with some given to us already. All right, so I want to see if we can take advantage of some of the labelings. Of course, this is lowercase b in this case because it's opposite of capital B, and all the other ones are already labeled for us. Now, they may not be, so if I ask you to complete a triangle and I only give you labelings on the things that are known, then you have to label things accordingly so you know how to apply the law of sines. Because you kind of see it's pretty dependent on the labeling of the sides and angles. Anyways, jumping right into things, we see that sine of C is, well, let's say this, C, which is unknown, is sine of this known angle 102, which is equal to, well, let's see now. We don't want to use A because we don't know the angle nor the side for A. So in that case, we'd have two unknowns, but we already have an unknown here. We only want to create a ratio or an equality of ratios, which is known as a proportion, with only one unknown. So with that being said, we need to use B because the angle B here is known and the side B is known. And remember, the side goes on top if the side is on top here. So that means it's going to be 28 over sine of that angle, which is 29 degrees. Now, the first thing I want to say is that It doesn't matter if you actually have the signs on top or on bottom, but I'm just kind of going by what is written here. And also here it says feet, but I'm going to leave that at the very end because we know all the sides will be also measured in feet, but the angles of course are in degrees. So now if you cross multiply, we get the C is equal to 28 over 20 sine of 29 degrees multiplied by sine of 102 degrees. And now it's calculator time. We can approximate this. Let's round it to 2 decimal places. It doesn't say what to round to, but I'm going to round to 2 decimal places and let's see what we get. All right, so I punched this into my calculator, making sure, of course, that I'm in degree mode in my calculator, and I got 56.49 feet, about. And again, I'm just rounding to 2 decimal places arbitrarily. Obviously, if it tells you specifically what to round to, use those guidelines. Otherwise, if you want to be exact, you could just leave it like this, and there's not really much else we can do. But in this case, I'm going to round, especially because this is kind of a practical type of problem because we're looking at measurements in feet. And I think that 2 decimal places I think is accurate enough. In fact, in this case, you could just round it to 56.5 if you like. But anyways, now that we have C known, we can go ahead and actually just replace this with what we know it to be now, which is 56.49 feet. So that's fine. And now something I didn't say that we actually could have done earlier is we can actually find this angle here. Because all angles in a triangle add to 180 degrees. Notice if you add 102 to 29, you get 131. So you need 49 degrees more to complete 180. So this has to be 41 degrees. And in fact, you know what? I probably should be labeling everything that we're discovering here in red. So let me write this 41 degrees in red. And let me also label this 56.49 feet in red. Awesome. So now, of course, the only thing we have left to find is A. And A is pretty simple because we're just going to apply again the law of sines, but involving A. So for sure we need A over sine of A, which we know that angle is 41 degrees. Okay. And what else? I'm sorry, it wasn't 41, it was 49 is what I said 49, but I wrote 41. Sorry about that. Okay. All right, well that sounds better. So now A over sine of 49 is equal to either C over sine of C or B over sine of B. I'm just going to use B over sine of B because those were given already. This was approximated, so since we're using something that's approximated on top of approximated again, our answer could be slightly off. You can try it on your own and compare to what I get here, and they may be actually very close, but let's see. Since we're rounding, they may be a little off. So it's going to be 28 over sine of 29, which is the angle opposite of that. So then, of course, cross multiplying gives us that A is equal to 28 over sine of 29 degrees multiplied by sine of 49 degrees. Now again, we'll use our calculator and approximate what this is, and then we'll finally be done with this example. All right, so I got 43.59 after rounding, and that's of course in feet now. And we have basically everything here boxed, but of course I'm going to write it in red like I said I would with the other ones. So it's 43.59 feet, and perfect. Now we're all set to go. The triangle has been completed. We know all of the sides and all of the angles. And now we'll move on to a few more examples. Right, so for this example, we have kind of this funny scenario where we have this pole that's tilted, and it's tilted towards the sun. We'll actually see why that's important in a bit, at an angle of 8 degrees, and it casts a 22-foot shadow. So let's try to draw that image. So normally the pole would be straight like this, but the pole is actually tilted a bit. So imagine it being tilted a little bit, and the direction that we're tilting it is in the direction of the sun. Okay, and this the angle that is tilted is 8 degrees. So this angle here is set to be 8 degrees. Now, how exactly I know that is kind of from the wording. If it's tilted a little bit 8 degrees, well, the word tilt implies that it's just a little bit, or else you may use a word like bent or something like that. I guess you could use tilt to imply extreme cases. But 8 degrees here, of course, is small. So the pole would normally stand straight at a right angle, but being tilted, we know that's the angle of tilt. And the floor here, we'll draw it to be the length of, let's say, 22 feet for the shadow. This is actually the floor, but imagine the shadow's over here. That's 22 feet. Now, the reason I know that it's important that we have the sun in the direction of the tilt is because the shadow that we're casting is going to be like this. In fact, let me kind of make a straight line here. In other words, this shadow is actually one side of this triangle, where this line just represents the straight line distance from the top of the pole to the tip of the shadow. And we have this angle of elevation from the tip of the shadow, which is this angle here, of course, which is given to be 43 degrees. And that's all the information we have actually. And from this, so this is a right angle. So in reality, this full angle here is 98 degrees, if that makes sense. And what we're asked to do is find the height of the pole. So I guess we can call this h for height. And then from here, we can use law of sines to hopefully solve for h. I mean, we don't really have too much information here, but remember, all you really need are angles and opposite side lengths. So we have h, and we have the angle opposite h. So we're for sure going to use those. So let me just write that we're going to have h over sine of the angle opposite of h, which is 43 degrees. Set that equal to another side length over the angle that it's opposite of, well, sine of that angle anyways. Now, the only side length we know is 22. Now, we actually can't find this length unless we knew something else, because this length is unknown, but this angle is. Which is kind of funny, because here it seems like, oh, we have this length known, but we don't have this angle opposite it known. But we actually do know the angle, because remember that in a triangle, if you know two of the three angles, you automatically know the third one just by subtracting their sum from 180. So the sum of 98 and 43, of course, is 142. Actually, it's 141. And there we go. And if you add 39 to 141, that leaves you with 180. So this is going to be 39. Let me just make sure I'm okay with that. Okay, so these add to 141, and then add to 39. Perfect. So that means this h over sine of this angle is going to be equal to 22 over sine of that angle. So it's 22 over sine of 39. And we're good to go. Now all we have to do is kind of do exactly what we did in the previous problem, and that's multiply both sides by this denominator to get h by itself. So h is 22 over sine of 39 degrees, multiplied by sine of 43 degrees, and then we can use your calculators to approximate this, and that's really going to be it for this problem. So now let's use your calculators and see what we get. All right, so rounding to two decimal places, just like in the last problem, I got about 23.84 feet. Just like that. And now we can move on to the next kind of example. Now the next one we're going to see, the camera kind of cut off there, but you can still see all of it, there we go, just to be safe. But the next problem we're going to take a look at is one that's still the same thing, but there's a subtlety that makes things not quite as straightforward as these previous two examples were. So let's take a look at that before moving on to the next idea. All right, so for this example, we're asked to only find the remaining side length, the angles we really don't care about, but as it turns out, to use the law of sines, we need one of the angles anyways. Remember that in order to find a missing side, you need, of course, the angle opposite that. So we still have to find an angle. So, of course, we're going to use maybe these two obviously are given, and then this to find this angle, and then we can finally subtract those to get this one, and we can go from there. I think that sounds like an okay plan. There is a little bit of a problem, but we'll have to see what the problem is as we go along. And we have to kind of keep a few things in mind. But before I kind of spoil the surprise, let's just kind of follow our nose a bit and see how far we can get. So let's see. So we see that we have this side given and the angle across from it given as well. So we have 22 divided by sine of 42 degrees. That I think makes sense. Great. And then I said we need to find this angle, but of course to find this angle we need this side. So I'm going to find this angle and then subtract 180 from the sum of these. And of course to do that we need 12 over sine of this angle B. And of course notice these side lengths are in inches now instead of feet from the previous two problems. And we don't know what B is actually. So we'll find B very shortly. right. So I think we're gonna be okay. I don't think there's actually too much to worry about. Well, let's see. So if we cross multiply and I guess we'll have to divide by 22, we'll end up getting that sine of b is equal to, let's see, so cross multiply, we'll have 22 in front of this, and then that'll be 12 sine of 42 over there. But then dividing by that 22 will give you sine of b by itself, and then b will just be sine inverse of that. So b is sine inverse of this thing, and of course you can cross reduce this if you want, or not cross reduce, but you can reduce this fraction if you want a little bit. 12 over 22 is 6 over 11 after reducing, but I'll leave it like this. We'll use our calculator now and see what we get, and let's take a look. All right, so rounded to 2 decimal places, my calculator gave me 21.41 degrees. And remember, this is of course in degrees because this is the angle capital B. Now, as it turns out, there's actually no real issue here. We, of course, well, we have this angle now, so we can find this angle. So recall that if we add these two angles together, let's see, 42, let's just add it here, I guess. Add it to 2141 adds to 6341. And then taking 180 away from this, well, 180 minus 60 will be 120. So 180 minus 63 will be 157. This is going to be 156.59. I'm, of course, trying to do it in my head, but if you use your calculator, you should get something pretty similar. Actually, this is a 116. There we go, because it's less than 120. But it doesn't matter how I'm doing it in my head, just use your calculator, you should get something like this. That's, of course, in degrees, so this legitimately represents capital C, the angle. And something I must say here is that we kind of got lucky because there's only one solution, but there are actually 3 different cases, and I'm going to try to describe kind of quickly the types of triangles we have here, because there's actually 3 types. So the first 2 types are where you have an angle given. So these are known as ASA and AAS. ASA just means the side that's given is in between those 2 angles that are given, and AAS means the angles are consecutive, and then the side that is given is not in between those. So something like where we have these 2 angles given, but then this side given, or something like that. And in fact, these 2 are what we saw from previous examples, so we don't really need to worry about these, and there's no weird case happening at all. The one case that is kind of weird, though, is, well, SSA, where we're given 2 sides but only 1 angle. And that's exactly what we have here, actually. Notice we have these 2 sides and some angle that's not in between them. And from here, it's actually very difficult to do. Now, in fact, I'm kind of curious what would happen in the SAS scenario. I don't think we're actually going to cover that, though. We could possibly do an example, but what I want to do is after doing this one, I know I said that this would be the last one before moving on to the next idea, but I think it would be in our best interest to actually go over one more after this, or maybe 2 possibly. Because for the SSA scenario, as it turns out, there are 3 scenarios. Either you have one solution like we will here, or possibly more than one solution, which sounds kind of funny, or no solution, which also sounds funny. But again, we'll take a look at that in a little bit. But now, of course, continuing this problem, we need to find this angle C, which we just did. So now we can safely say that C, lowercase c, over sine of capital C, 116.59 degrees, is equal to, let's use A and A, so it's 22 over sine of 42. Let's cross multiply to get C by itself, lowercase c that is. So it's going to be 22 over sine of 42, multiplied by sine of 116.59 degrees, and now we use our calculator and see what we get. Right, so my calculator actually gave me about 29.4, and that's a side length now, so this is in inches, and that's what we're asked to find, just this side. So we actually completed the triangle in the process, which is kind of interesting. So now, like I said, we're going to look at some more cases of what is called the ambiguous case, where it's 2 sides and an angle that's not in between those that's given. And it'll be kind of like this, but we'll actually take a look at 2 examples. So let's see what those entail right now. All right, so here we're asked to complete the triangle. We're not actually given any labeling here, so we can choose whatever labeling we want. I'll call this ABC like this. So of course this will be lowercase b, and this is a lowercase a, and this is lowercase c. So that I think will kind of help things a little bit. And now, what do we want to find first? Do we want to find an angle or a side length? In fact, remember you need one to find the other. So notice we have this side and its opposite angle, so we have to use this no matter what. So we're going to have to write 15 over sine of 85 equals, and we have 25, so we have to use 25 over sine of 8. So that's kind of a nice way to follow our nose to see what we have versus what we need. And perfect. So now we can solve for this angle, and we'll cross multiply, of course. And remember that when you cross multiply like this, you get 15 sine of A, but I'll hold off on writing that 15 for a moment, equals 25 sine of 85. And then we're going to divide both sides with that 15 just to kind of make things a little quicker. And then this implies that A is actually equal to sine inverse of this. Now we're going to use our calculator here and see what we get, and I think there may be an issue. So let's see. All right, so if you try to type this in your calculator, it'll say error domain or something like that. Basically, this number is not in the domain of sine inverse. Now, why is that? Well, it's actually because this number here, which is this inside, same thing, is actually 1.66 something, which is bigger than 1. And that's bad because remember the sine can be largest 1. It can be bigger than 1 from the graph of sine. The largest it can be is y equals 1. And the lowest could be similarly is negative 1. Okay, so that's the first hint of bad news. Now, what does that actually tell us? Well, it tells us that this is not actually a correct setup. In fact, I've misled you quite a bit. The actual drawing would look more along the lines of something like this, where we have 85 degrees, this is 25, and 15 is something like over here. So it actually doesn't even complete a triangle. It falls short just a little bit of actually completing a triangle, so a law of sines actually falls apart. So in this particular instance, this cannot be done because there's no such triangle. So let me just say no such triangle, and thus no solution. It's a pretty sad scenario, but in some sense it may be kind of good because, well, there's less work to do, but we have to kind of understand what's going on. So now there's one more scenario where we're given two sides and an angle. So let's take a look at that, and then finally we can move on to the next topic. All right, so now for this example, we're asked to complete the triangle. Very similarly to the previous problem. Now you may notice at first that 31 is way larger than 12, so I may possibly be misleading you again like I previously did, because this is like almost triple this size actually. So we'll take a look at that, but first let's just try to apply the technique of law of sines and see what happens. So we're only given this side and this angle, so the only place we have to start with is really just 12 over sine of that angle. Perfect. The other thing is we should label things, so let me label this again as A, B, C, just like that, so that this has no choice but to be lowercase b, of course measured in meters. This is then lowercase a because it's opposite of capital A. This is then labeled as lowercase c because it's, well, opposite of this capital C. Perfect. Awesome. So now that we have the labeling down, we can write some things out. Also notice that since we're given 31 for C, that actually pairs with the sign of capital C. So this has to be written like this. And we solved for sine of B last time when we got no solution. Here, let's see what happens. So we'll cross multiply and then divide by 12 simultaneously. So we get sine of C is equal to 31 sine of 20.5 degrees, and then divide by 12. And of course, C then, as we've seen before, is just sine inverse of this value of 31 sine of 20.5 degrees over 12. Let me make sure that sounds okay. All right, so there could be an issue. This angle could be actually bigger than 1. I don't think it is actually, though. Of course, 31 and 12, 31 is way bigger than 12. So if you ignore the sine part, yeah, that's bigger than 1. But sine of 20 is actually pretty small because 20.5 is closer to 0 than it is to 90. That was the problem with the previous problem we had, because it was sine of 85 degrees, which is close to 90, so sine would be close to 1, making the numerator larger than the denominator, making this not in the domain. But let's see what we get now, and let's see how we can continue from there. All right, so my calculator is giving me about 64.78 degrees. And here's where we have a little bit of an issue. So we could replace this with 64.78 degrees. In fact, I'll do that down here, just to kind of show you. But again, to try to give you a little more accurate depiction of what's going on, 20.5 degrees is pretty small like this. 31 is going to be way larger than 12, so it's going to be something like this. So we have 64.78 degrees. Something like that. And then we have 20.5 degrees. Now, actually, if you go back to not the previous example where there didn't exist a triangle, but the one before that, where we found sine inverse, we got a certain answer, and that angle was kind of small. Now, in this case, something kind of interesting happens. So in this case, there's actually two solutions, and here's why. Sine inverse of this is equal to that, but this is not the only angle whose sine value will give you this inside. So now notice this inside value, by the way, is 0.9047, so like 905 about. And there is another angle that will actually give you sine of 9.05, and it's actually just 180 minus this, which makes sense because if you look in the unit circle, there are two angles that correspond to the same positive sine value, one in the first quadrant and one in the second quadrant. So both of these have the same angle of 64.78 degrees in this case, but they correspond to, different complete angles. So they have the same reference angle, basically. In other words, we could get a possible obtuse angle. And you may think, well, how would that actually fit? And it would fit like this. So imagine just flipping this over so that this angle is 64.78 degrees, and then this angle here would have to be our kind of new angle C. So we have these two alternate scenarios. Either we have this weird inner triangle or we have this outer triangle. And this is what could possibly happen. That's why this is known as the ambiguous case, where you may get one solution like we saw in the first example, or zero solutions like we saw in the previous one, or two solutions like we're going to see here. Now, how we can tell that there was indeed only one solution in the first example we saw for SSA is because if you were to do 180 minus this, so by the way, 180 minus this, so this is like our alternative C, so or C is equal to 180 minus 64.78, which by the way is, let's see, it's going to be 115.22. Now this actually, if you add this to 20.5, it's less than 180. So if you were to take 180 away, or 180 minus the answer we got from the first example, you'd actually get a number that's, well, it's going to be in the hundreds as well, but it's going to be like 158, I think is what I got. And what happens is that if you were to add that to your angle, you will get over 180. So you don't have any room for doing this kind of swap here in that scenario. In this scenario, we do actually have that happening though, which is kind of funny. So we have these kind of two alternate cases for C. Either this is C or this is C, and we get this kind of split in the problem. Either we have this scenario or we have this scenario. And then you can go from there. So am I actually going to complete this? Let's take a look. So we got this being 64.78 degrees. I think that's okay. And here we got 115.22 degrees. This is 31. This is 12. This is 31. This is 12. I don't think this is actually very difficult to do. We'll just have to find the third angle here by subtracting the sum of these two. Same thing here, and then we can do one more law of sines to actually find the remaining side. But really what I wanted to say is that there's a possibility that you have two cases. So I actually won't complete this. I'll leave it up to you because I think it's fairly straightforward from here. I feel kind of bad because normally I like going through details like this, but I think this is okay enough. Because I really want to get to our next idea for us to be finally done with 8.1. So let's take a look at the next idea finally, and that'll be the end for 8.1 then. Alright, so the last idea now is really just an application of law of sines, kind of. This is actually used to find the area of any triangle. Now specifically the book says oblique triangle, so I'll use that language. Now what oblique basically means in their line of sight, I guess, would be a non-right triangle. So of course this is a right triangle. We have a right angle, and oblique just means non-right. Which this is actually true for. So we can actually find the area of a non-right triangle this way. But I believe we can actually find the area of a right triangle this way also, coincidentally. So let's take a look at that a little bit. I'm going to share with you the proof on how we do it. So the formula I'll leave as a little bit of a mystery for now, but we'll actually develop it a little bit here. So for the acute case, let's create a height and call that height h. Now recall that the area of a triangle is 1/2 base times height, and this base is b. So literally we have area is equal to 1/2, well, base times height. The only issue is we want to find it in terms of either a, b, or c, or the angles, not this made up h. But by law of sines, we know kind of what h is. Well, we don't necessarily know what h is, but we can actually write h as sine of, well, in terms of sine of c, for instance. So sine of c, notice, is h over a, so let me write that here. Sine of c is equal to h over a, and sine of a, for instance, I think that works out okay. So what's sine of a then? Sine of a is going to be h over c. So we cross multiply and solve for h, then we get that h is actually equal to a sine of c, or c sine of a. But in this case I'll use this one. So I use that, the h is equal to a times sine of capital C. So we plug that in here for h, then we actually get a formula for the area not involving a made up angle or made up height h. You could actually find the height if you wanted to, if you're given all of these sides and lengths. But in reality, all you really need are two sides and the angle in between those. That's kind of what this says. So if you take a look at that in terms of a, b, and capital C, we have 1 times a times b times sine of c, which is the angle in between a and b. And we can actually use this for any angle and any sides, so long as the angle is in between those. Just up to relabeling, really, or picking a different height, or using this guy instead of the other one. Well, actually, I use that one. Using this one instead of that one. There we go. Is what I meant to say. Awesome. So in other words, this is equal to 1/2 BC sine of the other angle, which is A, or 1/2 AC and sine of the angle in between those, which would be capital B. Now, this actually also does work in the obtuse case, much like we saw for law of sines, because this is very law of sine-ish, if you think about it, how we're replacing h with something involving sine of a known angle. And actually you can get something very similarly happening here. Again, if you take h to be sine of c, well, multiplied by a, because sine of c is h over a, so then h is equal to a times sine of c. So you'll get actually, well, I guess you'll get this one again. But again, that's proving it with the obtuse case. Now what about with the right case? Well, the right case, well, it gets a little weird. It's actually not too hard to show, but just know this, that all of the other cases are actually the same. The only one that's not is where we use the angle A. But it is kind of the same actually, because notice if we use the angle A, then it would be this scenario, 1/2 BC. But here C acts as the height, so we could just say it's 1/2 height times base. But notice sine of A, since A is 90, sine of 90 is 1, so this actually still holds. But for whatever reason, it's kind of a more obvious case for right triangles, so we don't really consider this formula for right triangles. So anyways, I'm going to box this formula up, and we're going to just see one example of this, and that'll be, again, the end for this video. So we want to find the area of this given triangle. We have this angle in between these two side lengths. Much like I said, is all we really need to find the area of a triangle. They're each measured in meters, so the answer will be in meters squared. So the area then will be 1/2 times the length of these, 52 times 90, times sine of the angle in between them, according to the formula we have established above. And then we can approximate, and that's of course going to be something meters squared. And yeah, let's just plug it in and see what we get. So I actually got quite a large number here. We got 2,288, so 2288.865, so it runs up to 87. This is actually an example from the book where they actually round this up to 2289 meters squared. Just because it's so large, you don't want to write too much, but I'm fine with us writing this. And let me just kind of make this look a little better. Meters squared, perfect, awesome. And like I said, that's the last thing I wanted to talk about finally for 8.1. There's no strange case here like there were for law of sines. Law of sines, of course, was the core topic in this section, hence why it was titled that and not areas or something like that. Anyways, we're going to take a look at a similar thing in 8.2, law of cosines, which is actually quite different than law of sines was. In my opinion, it's more useful and a lot more fun, but again, it's kind of all the same. But we'll take a look. Hopefully we'll have fun regardless. So I hope you enjoyed this, and thanks for watching. I'll see you in the video for that. See you then.